transformations, and other graphing techniques. Let's consider the following function f of x equals x squared, which we know has a graph that looks like this here. Using this basic graph, let's graph the following. What would 2 times x squared look like? Well, if you think about it, y equals x squared versus y equals 2x squared. The only difference would be that the y values here would be twice as tall, right? So just as an example, consider if we plugged in x equals 2. Here we're going to get y equals 2 squared, which is 4, whereas here we're going to get y equals 2 times 2 squared, which is 2 times 4, which is 8. So we're just taking the y value here and multiplying it by 2. So what that does, in effect, is it takes all the points on this graph and it makes them twice as tall. So the point here at the origin, 0, 0, that stays where it is, because of course 2 times 0 is 0. But when you plug in 1 here, you're getting 1, 1. Now you're going to get 1, 2. When you plug in 2 here, you get 2, 4. Now we're going to get 2, 8, which is up here somewhere. And so what you should notice is that the graph is taller. And the same thing happens on the other side here. So compared to the original graph, which looked like this, you can see that the graph 2x squared is twice as tall, or another way to see it is that it is more narrow. So that's what the number 2 does in front of the x squared. Now let's think about what happens to the graph y equals x squared plus 2. What does the plus 2 do? Well, once again, if you think about y equals x squared versus y equals x squared plus 2, the plus 2 is simply adding 2 to every single y value. So if you think about the graph of y equals x squared, which is this graph right here, every y value of every point on this graph is going to get shifted up 2 units. So for example, instead of being here, we're going to shift it up 2 units to here. Instead of being at this point, if we shift it up 2 units, we'll be here. Same thing happens on the other side. And what you can see rather quickly is that the graph here looks like this, right? So every point simply gets shifted up 2 units. So the graph is going to be like this. And this is what we call a vertical translation of 2 units. Or you can call it a transformation of the original graph, shifting it up 2 units. So then next we have to think about, what does this do? So notice now I'm adding 2, but I'm adding 2 inside of the parentheses before we are squaring. Well, the net effect of doing that is it's going to shift the graph either to the left or to the right. Now, which way do you think it would shift it? You would probably guess that it shifts it to the right, but that is actually incorrect. The plus 2 is going to shift the graph 2 units to the left. Now let's see why this is the case. On the original function, y equals x squared, if x is equal to 0, y is equal to 0. But on the equation y equals x plus 2 squared, what is the number x that we have to plug in here to make this equal 0? You should see that it's actually equal to -2, right? Because if we plug -2 in here, -2 plus 2 is 0, and then 0 squared will be 0. So the point that used to be here is now going to be shifted 2 units to the left. And the graph is going to be shifted along with it. So it'll look something like this. So if we take every point on this graph and shift it 2 units to the left, we get the following. And this is what happens in general. So now let's go ahead and take a look at the official rules. If k is a positive number, then the graph of y equals f of x plus k is going to move the graph of f of x k units up, whereas f of x minus k is going to move the graph k units down. If you add a number h inside of the parentheses or subtract a number h inside the parentheses, this is going to translate the graph left or right. X plus h translates the graph h units to the left, and x minus h translates the graph h units to the right. And finally, if you have y equals f of x, and you know the graph of it, multiplying f of x by some number a is going to stretch the graph vertically by a factor of a if the number a is larger than 1, and it's going to compress the graph vertically if the number a is less than 1. And finally, if a is negative, it will reflect it about the x-axis. So let's go ahead and take a look at some examples. Before we can consider actual examples of problems, we need to make sure that we know 6 basic graphs. Now, one of those graphs here is y equals x squared, which we've already talked about. But there are other graphs that you need to know. So what you can do is pause the video here and take a look at these graphs and take a look at the corresponding equations of the functions involved. But these are considered basic graphs, and we should have a basic idea of what each one of these graphs look like without having to plot a bunch of points. So let's go ahead and graph f of x equals the absolute value of x minus 2. First, let's bring in the graph of the absolute value of x as a basic function. So here's a picture of that graph. Now, notice that the domain of this graph is all real numbers. You can plug in any number x that you want, but the range is only values of y that are greater than or equal to 0, right? There's no graph down here. Okay, what does this graph look like? Well, we're subtracting 2 outside of the function, so we should know that it's going to take this graph and move it down 2 units. So if we move every point on this graph down 2 units, the resulting graph will look something like this. Now, as a secondary consideration here, the domain of our new graph is still all real numbers, but the range of our new graph is a little bit different. It's the set of all y such that y is greater than or equal to negative 2. Right? Because there are some y values on this graph that are below 0, but nothing below negative 2. Next, let's consider the graph of g of x equals x plus 1 quantity cubed. Again, let's bring in the basic graph for the cube function. So here it is. This one has a domain and a range of all real numbers, and more importantly, this is the shape of that graph. So we have to think, what is the plus 1 going to do to this graph? Well, the plus 1 is inside of the parentheses, so it's happening before we do the cubing of the function, what it says to do there. And so when it's inside, it's going to move it left or right. And it's the opposite of what you might think. So the plus 1 is going to shift it 1 unit to the left. And so if we sketch points, instead of being at 0, 0, it's going to be at negative 1, 0. Instead of being at the point 1, 1, it's going to be at 0, 1. And instead of being at negative 1, negative 1, we will be at negative 2, negative 1. And so this graph looks like this. So again, it's the same shape as this graph here, but it has been shifted 1 unit to the left. And in this case, the domain and the range are unaffected. Next, let's consider the graph of f of r equals 1 divided by r minus 4. Again, let's bring in the basic associated function here. And that would be the function f of x is equal to 1 divided by x. So how is this different? Well, don't let the variable worry you, right? It doesn't matter what variable we have here, whether it's an x or an r. What we have is the variable r and then minus 4. So what we have is we're subtracting 4 from the variable inside of the function, okay? So that would be very different from subtracting 4 after the 1 over x, right? So what we're doing is we're subtracting 4 inside. What that does is it moves the graph 4 units, in this case, to the right. Now, if you look at your graph of 1 over x, we have what's called an asymptote here. In other words, this is a vertical line that cannot be crossed, and that occurs at x equals 0. Well, that asymptote is now going to be shifted 4 units to the right, because again, everything on this graph gets shifted 4 units to the right. And then the actual shape of the graph itself, this part of it, is going to be exactly the same. So we're going to have a graph that comes down something like this. And on the other side, it's going to look something like this. And again, we're not looking for perfection here. We're looking for a way to be able to sketch these graphs very quickly by comparing it to the associated basic graph. Okay, so in this next example, we actually have two things happening here. So we have the function x plus 4 quantity squared and then plus 1. So in this case, we are talking about the basic function f of x equals x squared, which of course has this basic graph here. And then we're doing two things. We're adding 4 to x inside the function. That's going to shift the graph 4 units to the left. And then the plus 1 is going to shift the graph 1 unit upward. So rather than having the vertex of our parabola be at the point 0, 0, that point is going to get shifted 4 units to the left and 1 unit up. And then from there, it will look exactly the same. So the graph is going to go something like this. Okay? Now, let's talk about a very slight variation of this graph. What if in this function we had a negative in front? Okay, so what if I just put a negative sign in there? What would that do to the graph? Well, again, we already know that it shifts it 4 units to the left and 1 unit up. But what the negative is going to do is it's going to reflect that graph over the x-axis, okay? So technically what's happening is the graph gets shifted 4 units to the left first, okay? That's the first thing that happens. And then it gets reflected over the x-axis. So that means it gets shifted over here, and then it gets flipped upside down like this. And then the last thing is we add 1 to it. So what ends up happening here is the graph ends up being very similar to the one that we just finished a minute ago, except that it looks something like this instead. So that is what will happen when you have a negative in front of your function. So let's consider this one. We have negative 3 times the square root of u plus 4, and then plus another 4. So let's bring in the basic associated graph. So we are talking about the square root graph, which has this basic shape here. Let's think about all the things that are happening. This graph is getting shifted to the left 4 units. And then the 3 is going to be a vertical stretch by a factor of 3. The negative is going to be a reflection over the x-axis. And then the last thing that happens is the plus 4 on the end. That is going to shift it up 4 units. So let me just focus on the initial point here. If I take that point and I shift it to the left 4, that's going to put it over here. And then we're going to stretch it by a factor of 3. Now, I really can't show that until I start graphing it. So that's going to make it 3 times as tall, basically. Okay, so what does that mean? Well, if you zoom in here, this graph here, I go 1 unit to the right of the vertex, the graph is 1 unit tall. So if we were graphing 3 times the square root of x, what the 3 would do is it would make that point 3 times as tall. And so what it does is it just makes the whole graph taller, okay? So that's what that 3 is going to do. So we'll do that when we actually do the graph. But more importantly than that is this negative sign here. This negative is going to reflect the graph over the x-axis. And then the +4 is going to move it up 4 units. So we're going to go 4 units to the left. We're going to be going downward, right, because it's reflected over the x-axis. And it's going to be 3 times as tall, so it's doing something like this. But then it gets moved up 4 units. So what that's going to look like in the end is it's going to start right here. When I go 1 unit to the right, it's going to be 3 times as tall, but in the negative direction. And that graph is going to look something like this. Now, another thing to be aware of here is that the domain and range both changed, and they both changed fairly significantly. So over here, you can see the domain is a set of all x's where x is greater than or equal to 0. The domain here is a set of all x's such that x is greater than or equal to -4, right? Because you can actually plug in x equals -4 now. And then for the range, well, the range is all the y values. What y values do you get? Well, the largest y value that you get is +4. So your y values have to be less than or equal to +4. And for our last example, let's write the equation for the graph of what you see here. So this appears to be the cube graph. But what you can see is the original point, which is at the origin, seems to have been moved 3 units to the right and then 1 unit up. So what would the equation for that graph be? Well, let's think about it. To move it 3 units to the right, we have to subtract 3 from x before we cube it. And then to move it up 1 unit, we would simply add 1 after that. And this would be the equation that represents this graph. And that concludes this video lesson.